we can get started. Hello everyone, welcome to Lab 3. I hope people on Zoom can hear me okay. So,
Yes.
okay, thank you so much. Right. Welcome to Lab 3. Today, we are going to discuss network optimization. We'll go through different techniques like ablations, hyperparameter tuning, in order to get the best performance out of our model. And this is going to be particularly useful for your homework part 2s, including the homework 1 and the rest of the homeworks. So, the lab workflow is we have put a post on Piazza 238. You can download the notebook and the data for this lab from there, and you can save a copy of the notebook and the data on your Google Drive and perform the experiments that we'll be going through. So please follow the instructions in the notebook. We have 13 checkpoints. And by the end of the lab, you can respond on the same Piazza post as to how many checkpoints you completed. And please remember that this is not graded. The labs are designed to help you with your homeworks, so the checkpoints are not graded. All right. So as I mentioned, today we'll talk about how do we obtain the best performance from our model. And by best performance, we not only mean lowest training loss, we also mean the model should generalize better. So it is a well-known fact that machine learning and deep learning is a data-intensive industry. So a lot of the model's performance basically depends on data, and if we have more data to train a model, uh, it is going to learn and perform better. The model will learn and perform better. So the quantity matters, but what also matters at the same time is the quality of data, because the data that occurs naturally is not in a suitable form for feeding to the model and training a model on it. So there are a lot of data cleaning and pre-processing steps that we need to do in order to transform the data which is suitable for throwing at a model, right? So let's first discuss data manipulation. Uh, Even right now, as I'm speaking, my speech is being recorded in the form of audio waveforms. And let's say if you want to perform speech processing using deep learning, you cannot directly give the audio waveform to the model, right? We need to do some pre-processing, and usually the audio waveform is converted to MFCCs, which is mel frequency substral coefficients. This you already worked on this in your homework 1 part 2, where you worked with some audio data set. The only thing is we gave you the MFCCs, the clean MFCCs directly to work on, so you didn't really have to perform the pre-processing, but this is what happened at the back end. We pre-processed the audio waveforms and converted to MFCCs, and in real world, whenever you work with a data set and you're building a model, this is the initial step that you will have to do depending on the data set that you're using. So once you get clean data, the next step is data normalization. Data sets obtained may have different scales for different features, and in such cases, we have to scale the data so that we can get faster conversions. So as you can see here, the original data has, let's say, it has two features, one on x-axis and the other one on y. We first zero-centered the data, and you can see the two arrows which depict the scale of the two features. So you can see there is a difference in the scales of those two features. So we subtract with standard deviation and get the normalized data so that the scales are similar or comparable for both the features. Sorry. Oh, okay, wait. What is this? Okay, thank you. Okay. So yeah, the next step after data cleaning is data normalization, as we discussed. This is to rescale the features. And there are different techniques like z-score normalization, which we just saw. Apart from that, you could also do min-max scaling or standard scaling. And in your homework 1 part 2, you are using substral mean normalization. So this is a normalization technique for substral features. So it is computationally efficient normalization technique for robust speech recognition. And why is this helpful? Um, there could be a lot of variability in the audio data. For example, because of different speakers, let's say now I'm speaking and then Mani will speak. So the pitch, the tone, everything will be captured and it will be different for different speakers. Even different microphones can cause variability in the data. Environmental noise or the recording conditions also contribute to a little bit of variability, and we don't really want all of these factors to affect the performance. So we would like to reduce or minimize the distortion by noise contamination to get robust feature extraction. So this is why we do substral mean normalization on the audio data set. So here is some code blocks. We are just importing some libraries and we are getting the data. This is already given to you through the Piazza post. Um, this example is about image data set. So there are some normalization techniques that we have applied. And you can see these are the original images. And this is what we get after performing some normalization. All right. So the next part after you do data normalization is data augmentation. And data augmentation literally means increasing data, having more data. Because a lot of times it is not possible to obtain a sufficient amount of data required for training a model. And in such cases, we use data augmentation techniques to generate more data. And apart from generating more data, it also helps make the model more generalizable. So to intuitively understand this, let's say you have these three images, only these three images, you can apply some scaling or flip it across some axis, add some jitter and noise to create more images. And so this will effectively increase the data. At the same time, your model will not only learn to predict on clean images like this, but it will also learn on predicting using unclean, disoriented, noisy images, right? So this is how data augmentation also acts as a regularizer in a way. Right. So in your homework 1 part 2, the data augmentation technique that you used is time and frequency masking. So you had two parameters, time mask parameter and frequency mask parameter, which is depicted in the picture. So it basically hides the data on both the axes, either one or both the axes, so that our model is able to generalize better. It does not only memorize the training data. Right. So this was all about data manipulation. I hope it was clear. Are there any questions on Zoom? Okay. Yep. So moving forward, ablations. Once you have clean, normalized data, the next thing is to build your model. And it is a very painful step because unlike other things like learning rate or regularization, there is no theoretical argument as to which model architecture will work the best for your data set or the problem at hand. So you will have to experiment a lot with different model architectures. And this is why we encourage you to do this in a study group so that you can experiment multiple things at the same time. So yeah, from starting from lecture one, you might have understood that um, wider and deeper networks usually work. Um, uh, and So we are listing down some architectures based on the number of layers and neurons that you have. So please feel free to experiment with the different architectures. So you can have stack up layers with the same number of neurons to get a cylinder, or you can have pyramid. Um, I guess you'll get the intuition once you do a lot of experiments. But my one cent, like my advice, or maybe my intuition is, let's say if you're working on an image data set and you want to perform classification, this is what we'll also discuss in class. So initially, it's not really important for you to capture very detailed features in the data set. So it might be okay to let go of some features. So in that case, you can have a pyramid architecture, so that you will have less number of neurons, but the width will go on increasing, and you will be able to capture more detailed features as you go on. So it's up to you. Also, in, let's say, audio data set, you might not really want to lose any features. You would want your network to have same representation power across layers. In that case, maybe cylinder will perform better than any other architecture, but it's highly recommended that you experiment with the architectures and get some intuition around what works best for your data set and the task. Right. So yeah. While working on the part two of homework one, as I mentioned, you will experiment with a lot of possibilities, uh, like network shape, deeper or wider layers, also activation functions, because for some activation functions like sigmoid and all, you will have problem of vanishing gradients, so you can switch to ReLU or something like that. And then you could also add batch norm and dropout layers, which will be discussed later. Uh, and yeah, the other important point is, remember that you have a parameter limit to construct your architecture. So just because a wider and deeper network performs better, generally performs better, does not mean that you can just put any arbitrarily high number of neurons or layers in your architecture. So please stick to the limit for a particular homework. Okay. Before moving on, are there any questions or comments?
Yeah, just a little bit curious. For the architectures we mentioned above, just like I'm just noticing that because the output size is usually fixed. So do we usually narrow down before the output layer, or do we usually can connect the architecture directly with the output layer?
I think it will depend on your, like, the input and output will depend on your input size and the outputs that you want.
Okay.
Right. So, okay. So, all right, let's go to the next section. Before that, we'll just briefly discuss about the loss landscape. So a lot of times during lectures when we discuss gradient descent, loss function, optimization and all that, we do see a bowl-shaped curve, and the professor explains, how do we really want to approach, like how do we want to optimize. But in real life, the loss landscape does not look that simple. It is a complex landscape having a lot of valleys and cliffs. So this is how it will look. And in this complex landscape, you have to find the minima that works the best. Um, so having that in mind, we'll first talk about learning rate and schedulers. So what is learning rate? It is one of the most important hyperparameters while we train the models. It controls the weight update step taken by your model during gradient descent. So it directly influences the convergence of your model for a deep learning task. As you can see here, if the learning rate is too low, you will take small steps and it will take a lot of time to converge. And on the other hand, if the learning rate is too high, you will just keep bouncing around and you will not, it will be difficult for you to reach the global minima. So it's really important to have an optimum learning rate. So how do we achieve this? The learning rate scheduler adjusts the learning rate according to some predefined schedule during the training process. So generally, when you start training, you would want a high learning rate, and once you are closer to the minima, you don't really want to bounce and like just overshoot the minima. So you would want to have low learning steps, learning rate, so that you take small steps and approach the minima. So that's the general case. And you can have different schedulers to do so. For example, the first one is constant learning rate. And you can see here, this is like a step-based learning rate. So maybe you are just decreasing the learning rate with some constant factor. And there are different techniques like step learning rate, which will reduce the learning rate in steps. Then multi-step, exponential, cosine. You could also do reduce learning rate on plateau. So basically what you can do is tie the learning rate parameter with some metric, like usually validation accuracy. And if the accuracy is constant for some time, you reduce or decrease the learning rate. So yeah, there are different schedulers that you can try your hands on. And we would recommend you to go through the documentations and perform the ablations around this during your homeworks. Okay, so I hope it was clear. Are there any questions until this point on Zoom? Okay, Money will take care. Take.
Hi everyone, I'm Mani and I'll be continuing where Madhvi left. Madhvi discussed mainly about data normalization, pre-processing, learning rates and few schedulers. And I'll be continuing with normalization, mainly in the context of activations. So during training, we can't use the whole data set to take a step in the weights. So we usually divide them into batches and we use those mini batches to take a step. But the problem is a particular mini batch has its own distribution and it doesn't necessarily represent the training data's distribution. So what happens is each mini batch will have its own distribution. So when you pass them through the network, the activations will also have their own distributions. They live in their own space, and because of this, when you feed multiple mini batches through the network, there'll be multiple ranges of activations, and because of this, the model might not learn properly. So this calls for normalization, and there are many techniques in normalization, starting with batch norm, layer norm, instance norm, and group norm. We'll go through some of these in detail, and I'll leave the others to you. So let's start with batch norm. So our goal is normalization here, and usually batch norm is applied right after the linear layer and before the activation layer, but in principle you can apply after the activation layer as well. So what happens in batch norm is that, so you take the mean and variance of each features across multiple samples in the batch. For example, in the image given, we have 3 samples, like which are vertical rectangles that are concatenated, and the features are horizontal. Features are x1, x2, x3, and x4. So we take mean and variance for each features across the samples in batch. For example, for feature 1, we get mean of 4 and a standard deviation of 2.94. And for variance, we just need to square that. And we'll be doing that for each dimension. So what we are essentially doing is that we are making the mean of the mini batch 0, and we are pushing it to unit variance. So this is essentially normalizing it. But since we are making it 0 mean and unit variance, we are imposing a constraint on the model, telling that you should always come to this particular space or distribution. So we are removing some kind of flexibility from the model. So in order to give back the flexibility, once we normalize the mini batch, we also have two learnable parameters that are scale and shift, which is used to scale the normalized features and then shift, so that they'll have their own distribution. In PyTorch, batch norm is usually in the NN module, and it's called through batch norm 1D, and if it's a 2D batch norm, you can use batch norm 2D. So if you're using batch norm, it's been noticed that the model converges quicker, and you can essentially use a slightly higher learning rate. And also it regularizes the model because we are normalizing the activations. So if you see this code cell, we have an input with shape n, c, h, and w, where n is the number of samples and c is the channels, h is the height, and w is the width. If c is 3, it means that we have an image with R, G, and B channels. C are essentially the feature maps, the number of feature maps. So if you want to take the mean and variance with respect to batch norm, in the context of batch norm, we would have the dimension as follows, which is 0, 2, and 3, because we want to take the mean and variance for each features across every samples. That's why we don't have the dimension 1 here. And similarly for variance, once we take mean and variance, we subtract the mean from the sample and divide by the variance. And this is a simple implementation, but this has been implemented for you in PyTorch, so you just need to import them and use it. And you can fill the blanks if you want, but this is usually this blank will usually have the output dimension of the previous layer. Any questions in batch norm? Okay, and you will be learning the math behind the batch norm in Wednesday's lecture. So coming to layer norm, so the problem with batch norm is that the mean and variance that we calculate for a mini batch is dependent on the batch size. For example, if there are multiple samples in the batch size, for example, if the batch size is 2048, we'll have a good estimate of mean and variance. But if you have a small batch size, we might have a poor estimate. So this might lead to poor performance if the batch size is very small. And also, if you are working with any recurrent models, batch norm might not be a good thing to use, because recurrent neural networks operate on variable input size, and they have variable features. So batch norm might not be a good thing, because we have a fixed feature dimension when we are doing batch norm. So this calls for something called layer norm. So in layer norm, instead of taking the mean and variance across the samples for each feature, so we just take the mean and variance of each sample. For example, in this batch, which has 3 samples with 4 features, x1, x2, and x3, and x4, so we just take mean and variance of x1, x2, x3, and x4 for each sample. For example, for the first sample, 1, 3, 5, 7, we have a mean of 4 and standard deviation of 2.23. Similarly, for each sample, we do that instead of doing across batch. So if you see the difference with batch norm, we'll be taking the mean and variance for each feature across sample. But in layer norm, it's for each sample across features. So once we get these numbers, we do the same thing. We subtract the mean and we divide by the variance. And if you look at this code cell, it's the same thing, but with little change in dimensions. The input shapes are the same, N, C, H, and W. Since we are taking mean and variance across samples, across dimensions for each samples, so the dimensions will be 1, 2, and 3, which denotes C, H, and W. And since we are since it's layer norm, we omit the 0th dimension. And similarly, PyTorch provides a layer norm implementation, so we can just import that and use it. And the input dimension is also the same as the output dimension of the previous layer. These two are widely used, and there is another normalization technique called RMS norm, which is used very widely in large language models, mainly because of efficiency. But I'll not be covering RMS norm, but other than that, we'll be covering few other normalization techniques such as group norm and instance norm. So what in group norm, it's same as layer norm, but what we do in group norm is that we divide the channels into multiple groups, and the statistics, which are mean and variance, are calculated based on only the group. For example, if you have C channels, and if you want two groups, let's say the number of channels are 4, and if you want two groups, so we divide 4 channels into two groups. So let's say 0, 1, 2, 3. So 0 and 1 will belong to group 1, and 2 and 3 will belong to group 2. So we'll take the mean and variance for each group, and then we'll normalize them. That's what is being given. That's what is being. That's what is that in this cell. So G is the number of groups, and C by G will give us the number of channels in each group, and then we'll take the mean in these 3 dimensions. And instance norm is like a subset of group norm where the group size is literally 1. So in this picture, you can see that if the difference between group norm, instance norm, and layer norm, you can also think layer norm as a generalization of group norm where the group size is 3, whereas the instance norm is just the group norm with group size as 1. So any questions with normalization techniques? Okay. So let's talk about hyperparameters. So so do you guys know the difference between parameters and hyperparameters? Anyone in Zoom?
Hyperparameter, right?
Can you come again? I think you can go ahead.
Yeah. So I think in one perspective, parameter probably refers to weights. And a few others around.
Right. That's so as you said, parameters are the numbers that indicate how the model is trained, whereas the parameters are the learned weights and biases, and the hyperparameters dictates how the weights and biases become. So that's the difference. And if you are talking about model optimization, there are a lot of hyperparameters. So for example, batch size, learning rate, schedulers, dropout probability, context with respect to homework 1, and the size of layers, optimizers, and weight initialization. And playing with these will give you a better understanding of each, and at the same time, it might help you reach the high cutoff in P2s. So let's go through some of these hyperparameters here. So let's start with context, as this is very important for the homework 1 P2. So in homework 1 P2, you are tasked to predict a phoneme. So the audio is divided into frames, and you are feeding the model a frame with 28 features, and you're asking the model to predict what phoneme you can infer from this particular frame. But the problem is these frames capture only a short duration of audio, which is typically 30 milliseconds. So this is not enough for the model to infer what phoneme is there in that particular frame. So what we do is we provide some frames which come before that particular frame we want to predict, and some frames after the frame that we want to predict, which we essentially call it as context, and we ask the model to predict. So it's like you can think of something like, uh, mm, when I give you a lot, so it's like some context that I'm giving so that you can understand more about the thing that you're learning, and when I give more context, uh, it may introduce unnecessary noise or relevant information, and the model might not predict really well. So let's take an example where you're learning something and I'm trying to teach you something. If I throw you a lot of math equations and hard stuff, it might be hard for you to follow and understand what I'm saying. And at the same time, if I don't teach you much, and if I just say if I explain the whole concept in one single sentence, it will be hard for you to understand. So it's very important to have an optimal context size, which is not too long and which is not too short. And for homework 1 part 2, it's recommended to start with a default context size, and you can try playing around with it and find the optimal range. And the next hyperparameter that we would like to talk is about optimizers. And optimizers play a very important role in models performance, and the model's performance might be boosted by a great extent depending on what optimizer you choose, because optimizer is responsible for updating the weights of the model depending on the loss. So there are many optimizers provided by PyTorch, such as SGD, Adam, AdamW, Adagrad, and RMSprop. SGD has been used widely by a lot of people, but nowadays AdamW performs better than SGD. So you can start with Adam or AdamW, and if it doesn't work well, you can switch to SGD. And optimizers are usually defined like this, where all the optimizer algorithms are under the optim package. So you can import the optim package, and you can define the optimizer. For example, if you want to define Adam optimizer, you can go like optim.adam, and you need to give the model parameters that you want to optimize so that it knows that these are the parameters that it can update. And you also need to provide the learning rate, which we discussed earlier, and this will define the optimizer. And this is a typical training loop which we'll use for almost all homeworks. So what happens in a typical training loop is that first you need to zero out the gradients, and then you need to get the predictions, find the loss, and based on the loss you need to calculate the gradients, and the gradients are calculated using backward function. And based on the gradients, we need to take a step. So that's done by this line, and this line is like optimizer.step. And this will we are essentially telling the optimizers to update the model weights based on the gradients that we have calculated in the previous line. We need to do optimizer.zeroGrad before doing anything, because when we are calculating the gradients with respect to loss in this particular line, and when we are looping and coming back to this line again, the gradients won't clear out automatically. So the gradients accumulate. So let's say in the first pass, the gradient calculated was 2, and in the second pass, the gradient calculated was 3. If you don't zero out the gradients, the final gradient will be 5 when we are doing optimizer.step. So it's not optimal, and we don't need it here. But this kind of feature is there in PyTorch because it will be helpful in some situations, such as gradient accumulation, which we'll talk later. And if you run this cell, you can see how the gradient accumulates. And coming back to weight initialization, this is one of the topics that is overlooked in the area of deep learning, because it's done for us a lot of times, but it's essential to understand weight initialization so that you can debug your model when things go wrong. So when we are talking about weight initialization, we are essentially talking about the weight matrices and the bias value that are used in the model. So let's start with this question. Why don't we initialize the weights of the model with zeros or some constant values? Anyone? Anyone from Zoom? Okay, so let's say that if you initialize the weights and biases with 0, uh, and if you do a forward pass, all the activations will also be 0. So if the activations are 0, the gradients will also be 0, which means that we are not doing any updates. And this problem is widely called a symmetry problems. So since we are getting 0 gradients because of 0 weight initialization, why not initialize with a constant? So let's say that we initialize all the layers with some constant. So we do a forward pass, we get some value, not 0 this time. And if you're calculating gradients, since all the neurons in a layer have a constant value, every neurons will get the same update, which means that every neuron will have the same weight even after taking the step. So it's essentially having one neuron. So even if you have 10 neurons in a layer, since all the values have the same weights, it's equivalent to having one neuron. So since 0 and constant is bad, why not initialize with random values? So let's say that we initialize with random values that we sample from a normal distribution with mean as 0 and with some variance sigma square. This is better than the 0 and constant initialization, but we still have a parameter here, which is the variance. And it's very hard to choose this parameter because let's say if the variance is very small, and if you have some activation functions like tan h, the forward pass will give activations which are very small because the weights will be close to 0. So the activations and the output will also be close to 0. And if you are doing a backward pass using those, the updates will also be very small, which is not optimal. So let's go to the other extreme where we have very high variance. If you have very high variance, it means that the weights are essentially big. And in case of tan h, for example, since the weights are big, the output values which we get will be saturated and will be very close to 1 or -1. And the derivative around those points are very small, which means the gradient is very small, so the weight update will also be very small. So this proves one thing, which is that the variance of the output matters a lot. So most of the weight initialization involves finding this particular variance value. So there are multiple works that have been done by Lekun, Xavier, Glorot, and Kaiming He. And Xavier and Kaiming initialization are one of the popular initializations. And the initialization used by PyTorch itself is based on Kaiming's uniform initialization. If you look at the linear code, you can find the initialization, and that's essentially this formula where they, in Kaiming, they sample the weights from a normal distribution with mean as 0 and with some variance. And one thing that's common in both Xavier and Kaiming is that they consider both the input size and output size when initializing the weights in a particular layer. And you might, if you're facing some issues such as nans in the forward pass, even before beginning training, it mostly means that there is some issue with weight initialization. So this is the code cell where you can play around with weight initialization. And it also depends, and choosing the weight initialization technique also depends on the nonlinear layer that you're using. For example, Kaiming initialization is proved to be better with ReLU and the variance of ReLU, whereas Xavier initialization is proved to be better with sigmoid and other activations such as tan h. So you should keep those in mind when you are choosing initialization technique. And the next one is overfitting and underfitting. I bet many people might have faced this in P2. And even in homework too, many people would face this for sure because the data is designed to be like that. So before getting into that, let's discuss both two common terms, which is bias and variance. You might have come across bias and variance when you, you are studying about perceptron algorithm and gradient descent. So bias is nothing but the error of the model. Since it's an error, we want the model to have less bias, and uh, variance is how much the model is sensitive to the training data. And if the model has high variance, it means that it's very sensitive to the training data, and it has learned a lot from the random noise which is in the training data as well, which we don't want. So we want the variance to be low, and yeah, we want both the variance and bias to be low. But in an ideal world, it's very hard for both the variance and bias to be low. So there's always a trade-off between bias and variance, and that's what is called as bias variance trade-off. And in context of those two, we have something called overfitting and underfitting. Overfitting happens when model learns too much from the training data. In other words, overfitting is something that happens when model memorizes every pattern that's present in the training data. It even memorizes the random noises in the training data that is not even required. So when you use the trained model which has overfit and test it on the test data, you will be seeing a very large difference in the numbers. The training accuracy will be very high, whereas the test accuracy will be very low. If you see that scenario, it mostly means overfitting. And there are many techniques to prevent overfitting. We'll cover some of these techniques in this lab, such as regularization, early stopping, and using dropout. And the next one is underfitting. Underfitting means the model failed to capture all the underlying patterns from the training data. So if you look at this graph on the right, so initially the model will not know anything, so it's underfitting. As we run for more epochs, the model will learn, and the model will try to fit the data. But if you run for more epochs than required, the model will start memorizing the training data, which is bad. And when you give a new data to predict, it will just give some crazy results which might hurt the accuracy. So underfitting and overfitting are both phenomenon that's not optimal. So we need to find the right spot where we need to stop the training. And some techniques to stop overfitting is dropout, regularization, etc. And we look at dropout first. In dropout, the term dropout, it just literally means we are dropping some neurons in a particular layer. So we define dropout using nn dot dropout with some probability p. Let's say the p value is 0.5. It means that for every neuron in the layer, there's a 50% chance that the neuron is dropped or turned off. So when you do a forward pass, that neuron will have 50% chance of getting turned off. And since it's probabilistic, every forward pass will have a different set of neurons that are dropped or turned off. So this means that we are forcing every neurons to learn something new in every forward pass. And this will help the model to generalize better. And when you're implementing in PyTorch, it's under the NN module, and you can essentially call dropout with some dropout probability, and that will do the work for you. And other techniques include early stopping. So early stopping, as the name says, we stop the model before it overfits. But the main question is, how do we tell if the model is overfitting or not? One way is to tell is that when the train accuracy increases, but the val accuracy decreases, the model is starting to overfit. But I can't just say it based on one epoch or something, because it can be random or it can be a coincidence. So what we do in early stopping is that we define some variable called patience. So if the performance doesn't improve for the number defined in patience, we stop the model. So for example, if the patience is 2 here, so we'll check the val accuracy and val accuracy for every epoch, and we keep a count of how many epochs the val accuracy didn't improve. So when the val accuracy didn't improve for 2 epochs, we'll stop the model and we'll save the model before 2 epochs. And that's what is done in this loop. So in this line trains 1 epoch, this line calculates the val loss, and then we keep track of the best val loss. If the val loss doesn't improve, we have a counter which keeps on increasing. And if the counter is greater than patients, we just stop the model and then we load the previous best model. And this is early stopping. Any questions so far? Okay.
Yes, I have a question.
Mm-hmm.
Okay, so what is the optimal number of patients that you can define before dropping out? Because sometimes when you wait for a while, you can still see some improvement. So what I want to know is how long should you wait before you stop?
Wait, I didn't get your question. Can you come again?
Oh, okay, I was saying, what is the optimal patients that you can define for before you stop your model?
Okay, it depends. I usually go with 4 or 5 because it gives me a good range to test accuracy. 2 is very low because uh, it can be a coincidence where your val accuracy doesn't improve. So it's better to have 4 or 5. Does it answer?
Okay, thank you. Okay.
And the next technique is gradient clipping. So sometimes what happens is that when you're doing backward pass, the derivative calculated will be too high, so the next step that you'll be taking will change the weights of the model to a great extent. And we don't want the weights of the model to be changed to a great extent in one single step. And this might happen if a batch has a noisy data, coincidentally. So just because a single batch has a noisy data, we don't want to change the entire model drastically. So that's where gradient clipping comes. So as the name suggests, we just clip the gradients based on some min value or max value. And we also can clip the gradients based on the norm of the gradients. So these are the 2 techniques that are given by PyTorch that you can use. And I would suggest using it in almost all homeworks because this is a very common problem. And the next technique is regularization. So what happens in training is that sometimes the weights just blow up, and we don't want the weights to blow up. And if the weight blows up, this will lead to overfitting, and this might lead to gradient explosion problem. So what we do is we regularize the model. By regularization, what I mean is that I just penalize the model for having bigger weight values. So we have the normal loss, which is this, and in addition to that, I also calculate the norm of the weights, which is this, and I say that if the weights become more, I need to penalize the model, and this lambda is the regularization constant, which defines how much I should be penalizing if the model gets bigger, and this half is just here to cancel out the derivatives. And this is usually passed as a parameter which is called weight decay when you are defining optimizer. So you can define an optimizer called Adam and give the parameters that you want to optimize along with the learning rate, and you want to say that you need to regularize with a constant 0.1. And regularization also prevents overfitting, so it might be a good thing to try. So those are all the techniques and the hyperparameters. And coming back to homework part 2, there is since the data set is fairly large, it will take a lot of time to train the models, and you might come across a lot of memory issues and compute issues. So one way to solve these things is to have mixed precision training. So mixed precision training is nothing but using both FP32 and FP16 during the training process. So PyTorch provides 2 things called AMP, which is automatic mixed precision, and gradscaler, which is used for scaling and descaling laws, which we'll talk later. And we use both to perform mixed precision training. So what happens in mixed precision training is that we have a model with full precision. Here, full precision means FP32 and half precision mean FP16. So we have a model in F32, and we make a copy of this model in F16, and we perform forward pass in this F16 model. So, so the activations will also be F16, and we calculate the loss, and based on the loss, we calculate the gradients, and the gradients will also be in F16. So once we calculate the gradients, which are in F16, we use these F16 gradients to update the original model, which is in F32. And this process repeats again and again. So, but the problem here is since the model is in F16, which is half precision, there might be a problem of underflow when you're calculating the gradients, since the loss might be very low. So what PyTorch does is it scales the loss before calculating the gradients. So that's where grad scaler comes into picture. The grad scaler will scale the loss, and once the gradients are calculated based on the loss, the gradients will be descaled since it's scaled earlier. And once it's descaled, it will be used by the optimizer to update the weights. And this helps us in achieving a faster training, and it uses less memory. Since it uses less memory, it also means that we can have a batch size of a higher number. So this is how mixed precision training is implemented. So we define the grad scaler here, which is used for scaling and descaling the loss value. And this autocast is the context manager, and whatever comes under this context manager is done mostly in FP16. If it's not done in FP16, it will be done in FP32. It will decide for you whether to do the operations in FP16 or FP32. So in this case, we are calculating the outputs, which are activations in half precision, and also the loss in half precisions. Since the gradients can underflow, we need to scale the loss, and this is done by scalar.scale loss, and then we are calculating the gradients. And we use the same scalar object to take a step with optimizer. So internally, this will descale the gradients, and then it will take the step. So, and this scale is dynamically decided by grad scaler. So every time we take a step, we also need to update the scaling value, and this is done by scalar.update. So for example, if it has scale more, and if it leads to overflow, it will know that it will need to reduce the scaling value. At the same time, if it has reduced the scaling value, and if it leads to underflow, it will increase the scaling value. And some general tips for homework too is that it's impossible to try all the combinations of hyperparameter in a given limited time frame. So it's better if you form a good study group and collaborate within the study group. So the first thing that I would recommend is to have a set of hyperparameters that you want to fine tune, and try dividing that and let each person from your study group do separately and share the results with each other. So when it comes to sharing, you can either create a team in 1B and share those runs, because if you create a team, every member of your team can see each other runs, and they can analyze the results, and they can decide which works and which doesn't work. And 1B also has a good feature called sweeping. So you can define all the hyperparameters that you want to tune, and once you decide all those things, you can just call the 1B to sweep those hyperparameters. It will run all the hyperparameters for you, and it will give you the results. And based on that, you can analyze and infer which is good, which parameters are good, and which hyperparameters are bad. And when you're doing hyperparameter tuning, I would recommend you to start with a subset of the data set. Do it for few epochs. You will know if that particular combination of hyperparameters is bad or not. If it is bad, you can definitely eliminate it. If it is good, you can go ahead and try training with the full data set. Yep. And coming to the end, I would again say use the study group wisely. Don't do it all alone. It's very hard because there are many combinations. And try to use your intuition and the theoretical knowledge to choose the right hyperparameters, like how to choose learning rate. Like let's say you start with some learning rate and and you see a gradient explosion. So based on your knowledge, you should be able to decide that you need to decrease the learning rate or add gradient clipping. And you also need to choose a good batch size. So choosing a batch size is always tricky, at least to me, because there is always a trade-off between maximizing the GPU usage by having a big batch. But at the same time, when you have a very big batch, you're essentially removing all the noises uh, that are in the batch, which might hurt the generalization of the model. So uh, it means that bigger batches doesn't always lead to a better performance. So you might need to find an optimal batch size. But I would suggest you to start with a bigger batch size so that you utilize the GPU to the full extent. And then if it doesn't perform well, you can try decreasing the batch size. And as usual, don't forget optimizer.geograd to which clears the gradient, and use task.inference mode when you're evaluating, because this will disable the dropouts and other stuff that are not needed during inference. And experiment with multiple schedulers such as cosine annealing, step LR, and reduce LR and plateau. You can also use warm-up for schedulers. And warm-ups are better with large models because uh, you don't make a sudden update with the last learning rate. It gradually increases up to some epochs, and from there the learning rate decays. And if you face some memory issues, you can always use task CUDA.empty cache, which will free up the GPU memory. And make sure you also maximize the number of workers. It depends on the GPU. So I think if you're using V100 in PSC, I think the maximum workers for V100s is 5. And for Colab, if you're using A100, I'm not sure, but it should be somewhere around 8 to 12. But if you go more than the recommended numbers, it will throw a warning, so you can tune based on that. And yep, and don't forget to divide the work among your study group and make use of the study group. Any questions?
Yeah, I had a question.
Mm-hmm.
So the result that we see on Kaggle on the competition is just like 40% of the test data. So how can we like guarantee ourselves that the cutoff that we got now will be what we will be graded with? Like for instance, in the 40% test data, if we pass that cutoff, but in the 100% of the test data, if it becomes lower, it becomes very difficult for us to evaluate ourselves and guide ourselves in that kind of scenario. So, do you have any recommendation on how to overcome that, or is there any way around it?
Yep. Yeah. So before answering your question, so the main reason to not show the private test set is to test how generalized your model is. So the first thing that I would recommend is to check the difference between the val accuracy that you got locally and the test accuracy that you got on the 40% of the test set. So if the difference is too much, it mostly means that your model is overfitting. But if the difference is not much, it's fine. And I would recommend you to get the test accuracy like 1% above the recommended accuracy. For example, if the high cutoff is 87, it would be safe if you have an accuracy of 87 in the 40% of the test set. So if you follow these two things where you have some extra accuracy, and if the accuracy difference is not too high, you should be good. Does it answer your question? Any more questions? Okay. I think we are done. Thank you for attending the lab. See you guys on the Monday's lectures.